Yesterday, we were talking about analytic functions, or very well behaved functions. And we did mention a few of the reasons why I call it a very well behaved. And if you recall, we did talk about the following while talking about the mappings that satisfy the CR equations, that these quantities, they were related to each other, and then we obtained, and we showed that if one of them is moving in one direction, the other is also interconnected. Delta U by delta X is connected with delta V by delta Y. This delta V by delta Y is not going in any way that we want. It is connected with your delta U by delta X, and so on. And then later on, we also gave some other examples. We did consider the sufficient condition that only this much is not sufficient, that these should satisfy the CR equations, but something more is also required. Namely, it's not that at this point and at this point and so on, it satisfies CR equation, but even here, there is a continuity between these. It shouldn't happen that something is happening here, all that is okay, and then here suddenly something else happens. There is a gradual continuity that is there. So that does indicate that the functions have to be well behaved. Only then it is possible. Next, we did consider Cauchy's integral theorem, and that normally in real time, it's quite possible to move from one point to the other point. Whereas when we are talking about on a curve C, on some curve C, from one point to another, there are different ways in which one can reach. And to get a unique answer, we do require the function should be well behaved. There should be simple. Analytic function should be an analytic function, and of course it should be simply connected. There, of course, this part also is there, that simply connected is also an essential part that we did discuss last time. And this was the interesting result where we had all stopped, that if we have a region and this is gamma, and that's point A, the function is analytic here, then f of A is given by this particular formula. So, and of course, naturally, when I say that it is depending on this quantity, this Z is variable on gamma, that is on this. And obviously, I'm interested in this quantity. If I'm taking it as A, and there's your Z here, it's a Z minus, say there's the point Z here, that we are talking about this particular quantity, Z minus A. If the variable Z is here, it is Z minus A, and so on. And naturally, if this is the point B, your Z minus B would be definitely different, and the corresponding answer would be changing. Or in other words, of course, we can even calculate f of B. It would be 1 over 2 pi I, integration over gamma, f of Z over Z minus B, dz. So observe every point here can be calculated. Whereas in continuity, there was only one point which we can calculate. If there's a gap of just one point, it's possible. In the real line, or even in the complex plane, if it is discontinuous at one point, I can find what the answer is going to be. But if there's a gap this much, then it will not be possible for us, and the point is somewhere here, or we have moved only till here, then I will not be able to get what the answer is going to be here. But here it's quite possible. So from that point of view, these analytic functions are very well behaved functions. Now let's go ahead with some more results. It also says that it is not only the FA, I can even calculate FK of A with the same gamma that we had here. I can calculate Fk of A, that's your point A. So I can calculate Fk of A. There's a formula for that, k factorial over 2 pi I, integration over gamma, Fz over Z minus A, dz. Observe here that it is not only Fa that I can calculate from the earlier result, even the first derivative can be calculated, and it also says something more. It says if f of A is there, that of course we can do it, even the derivative will exist at the point A. In fact, this particular function, f dash of z, is going to be analytic. So if a function is analytic once, its derivative and everything are again going to be analytic. So again, observe this quantity about well-behavedness. If the function is analytic in a region, then its derivative is also going to exist, and its derivative, or it's going to be analytic, and the derivative of that is again going to be analytic, and so on. So once analytic, all the derivatives are going to be analytic. And at that particular point, we can also calculate fk of a. So, and that naturally would be possible if the function is very well defined. It is in fact an analytic function. Let's move on. Next, LIOUVILLE'S theorem. You have studied it, that a bounded entire function is a constant. To remember it, the same thing is happening here. If fz is the entire function, and if fz is less than equal to m for some finite number, then fz is going to be constant. Just try to visualize it. If I take some point from here, and it is mapped somewhere here. Say this point is mapped up here. If this is a point, maybe a little far off, I would expect it to move somewhere here. Maybe somewhere here, or maybe here. The point is here. I would like it to move somewhere here. Because if I want the function to be well behaved, if it is not well behaved, the point may move arbitrarily. Sometimes here, and so on. But since it is well behaved, I expect it to keep on going further away as it was going on. Unless, of course, it remains at the same place. That is what we expect. And that is what the LIOUVILLE'S theorem says. In fact, this also is linked with your maximum modulus theorem that we should be talking about a little later. So this is what we expect, that if the function is not bounded, then in fact, if the entire function, the bigger the value I take, the bigger the corresponding answer that we are going to get. And if it remains bounded at a certain state, it means it has to be only a constant function. Now, we had proved this CAUCHY'S theorem, which said that if the function is analytic, in a region D, then integration over this quantity in a simple closed curve is going to be 0. So obviously, the first question that comes up is, if this is true, let's say there's a gamma. If this is true, is the function going to be analytic? And we can expect that if it is well-defined function, or it's going to be a good function, only working here will not give us the answer. It should be everywhere. It shouldn't happen that here it is okay. Somehow we have been able to do it, and then later on something else happens here. That should not be. So everywhere, every closed curve, if that is true, that is, if I can reach from one place to the other place without any problem, or giving the same answer by any way and that I like, only then the function is analytic. So that's your Morer's theorem. If fz is continuous in the region D, and integration of gamma fz dz is 0 for every piecewise differentiable closed contour in D, then the function fz is analytic and is very well behaved. Let's look at, we have studied what are known as harmonic functions. Let G be an open subset of C. A function u from G to C is said to be harmonic if u has a continuous second order partial derivatives and delta square u by delta x square plus delta square u by delta y square is 0. And there's a theorem that you may have studied following: if f is u plus iv is an analytic function in D, then u and v are harmonic. So observe this theorem. If f is u plus iv, naturally two parts are in it, real and the imaginary, is analytic in a region D, then U is harmonic. That means U satisfies this statement. Delta square by this quantity. Similarly, V is analytic. V is also harmonic. So it will satisfy delta square V by delta X square plus delta square V by delta Y square is equal to 0. But now look at what does this suggest. It says this portion, the second derivative, delta square U by delta X square, is related to delta square U by delta Y square. So if the function is well behaved, then your U and V satisfy this. Observe this relation and your Cauchy-Riemann equation. Let me just go back to it. In Cauchy-Riemann equation, you connected U with V. We said that these two quantities are interrelated, U and V. Now what we are saying is the function is well behaved. Even in U, with respect to X and with respect to Y, they are interrelated. So you can see the beauty of that portion, that it is not only these two quantities being interrelated, even within themselves, because there's a factor of 2 of these, similarly here, they are also interrelated. So let this be true. So U and V are going to be harmonic. That means U satisfies this condition. Delta square U by delta X square is minus delta square U by delta Y square. So the rate of change here is this. And if you try to connect it with your physics, a little of physics, it says it's the second derivative. And if you remember, the second derivative gives you an acceleration. So it says that even the acceleration that we're talking about is related. So delta square U by delta X square is minus delta square U by delta Y square. That is within, of course, U and V were already related by the earlier CR equations, but now we are saying that even in this, the way the things are changing are again interrelated, and delta square U by delta X square is minus delta square U by delta Y square. Similarly with this quantity. So the beauty of the way graduate is not arbitrary, there is a relation that is always there. So that's why I call it as well behaved. They don't move around arbitrarily, but in a well organized manner. Let's take the Taylor's theorem. Let Fz be analytic in a region D. Let A be in D. Let delta be greater than 0. We said that in Z minus A less than delta subset of D, Fz is given by Fa plus Z minus A F dash A plus Z minus A square 2 factorial and so on. This we normally tell, but try to analyze this statement. So what we are saying, we have a region and there's the point A, and then we have a disk with center this, and there's the point Z. Right? Now look at the structure that is here. We have Fa, the value at this particular point, F dash of A, derivative at this same point, F2 dash of A, same, F3 dash of A, the same, and so on, even Fn of A. And then of course, the other portion is in reasonable. It says Z minus A, Z minus A. In the second one is Z minus A square by 2 factorial, Z minus A cube by 3 factorial, and from here to here. So basically, if I know the structure at one point here, at A, that is, if I know FA, F dash A, F2 dash A, F3 dash A, and so on, your FZ can be calculated. Of course, that's your A. Of course, Z that we are taking here. So naturally, this quantity, if I want to calculate FZ, naturally this distance has to be taken into account. If I want to calculate Y, so F, that Y minus A distance has to be taken into account. But this point remains the same. This point is FA, F dash A, etc. So theoretically, what I can say is if I know a structure, if the function is well defined or is a very good function, then if I know the structure at this one particular point, then this particular point can be calculated. If the function is, say, well defined, or in fact, a very beautiful function. Second. If the function is well behaved, in that case, we can have that situation. And it's true for every Z in that disk. So Z can be here, or it can be here, or it can be here, anywhere. I can calculate FZ. And that's possible only when we are talking about these terms. Next, there is this theorem again. If Fz and Gz are analytic in a region D, known as the identity theorem, let A be a subset of D which has a limit point in D, and Fz and Gz be equal to Gz in A, then Fz will be equal to Gz in D. So look at it. We have the region D and a small piece here, call this as A, with its limit points here, which has limit point inside D. So it has limit points inside D. That, or what we are trying to say, it may even be looking like this. Some are more complicated diagrams, but anyway, so limit points must be inside D. Now, in that case, observe, it says that if the two functions f and g are the same here, if the two functions are the same, f is the same as g here, and if they are well behaved, naturally, we expect them to be the same a little more ahead, the same a little more ahead, the same everywhere here, the same here, or in general, same everywhere. And that's what it says. Of course, coming from this side is no problem. Coming from this side is no problem. If Fz is Gz in the whole of D, obviously, Fz and Gz will be equal in this part. But the importance comes up if it is different from, if it is here, and then we are moving in this direction. So let Fz and Gz be analytic in a region D, and where A is, of course, is in a region D. Let A be a subset of D, which has a limit point in D, it's a subset. And let Fz be Gz in A, then Fz is equal to Gz in D. In fact, corresponding this, the similar type of resolution is our next theorem. That gives a little more idea. Let Fz be the principle of analytic continuation. Let Fz be analytic in the region D, then the following statements are equivalent. For some A in D, Fn of A is 0 for all n in A. And Fz is 0 in a neighborhood of A, and Fz is 0 in the whole of D. So we are having a region D. There is one point, call it as A, on which I know the structure that somehow, by some method, I know Fa is F dash of A, is F2 dash of A, and so on. And all of them are 0. if that is true, this quantity is true, just looking at the structures at the point A, nowhere else, I can say that at this particular point, the answer is going to be 0. F of z is going to be 0. So it's going to be 0 in a neighborhood of A, because all are equivalent. So in this neighborhood, it will be 0. And because they are equivalent, it says that it is not only 0 here, it is going to be 0 everywhere. Of course, proving this from here to here is quite simple. If 0 everywhere, obviously it is going to be 0 here in a neighborhood. And this 0 in a neighborhood implies you're at the point A, it is going to be 0. But even the derivative are going to be 0. So all these three conditions are equivalent conditions. And this happens only because the functions are well behaved. Just looking at one point, I'm able to tell what is happening everywhere. There's another interesting theorem known as the SCHWARZ'S lemma, which says the following: let fz be analytic in mod z less than 1, with f of 0 is equal to 0. If f of z modulus is less than 1, mod z less than 1, then fz is less than or equal to mod z in mod z less than 1. And if f of z naught is less than or equal to z naught, no, this is if f of z naught is equal to, that's equal to, if f of z naught is equal to z naught for some z naught in 0 less than mod z less than 1, then fz will be equal to lambda z in mod z less than 1, where lambda is a constant with mod lambda equal to 1. And if fz is not of the form lambda z, then f dash of 0 is less than 1. Again, let's try to look at it geometrically and see what is happening. We are having a mapping from a unit disk to a unit disk. That's the first thing. The mapping is from here to here. It is a very well behaved analytic function with 0 going to 0, with 0 being mapped to 0 under f. 0 goes to 0. Let fz be analytic in mod less than 1 with f of 0 equal to 0. If fz in modulus is less than 1 in mod z less than 1, and in fact, that statement is here. It's a mapping. It is analytic here, and the answer lies mod fz is less than 1. So the quantity lies inside this portion. That's your point 1. So fz is analytic in mod less than 1 with 0 going to 0. And if the answer that we get is always inside the unit disk, then fz will be less than or equal to mod z. So geometry, again, let's try to look at it. If this is there and that's 0 and that is 0, then the image of this is going to be, and it's given that the answer is inside this region, the unit disk, then the image of this has to be something smaller. This is what it says. If mod z, fz is less than 1 mod z, then fz will be less than or equal to mod z. So if I take a point z here, so mod z is this quantity, the corresponding mod z, fz will be something here less than this or equal to that quantity. So observe what it says. It says that the quantity that I'm taking here, say a point which is nearby, will not go to a very far off place. The further point that we have will be within that region. So I'll just draw the two diagrams, almost of the same size. They are the unit quantities. We had the point here. It says if I have a point somewhere here, the corresponding value that I take, the length of this portion here, fz, would be less than that much. So it would be somewhere here. Similarly, if I take a point somewhere here, the corresponding point would be still nearer, maybe somewhere here, and so on. This is what it says. It's not arbitrary, that a quantity from here, any point, moves to anything that I want. That is not allowed. So this is what it says. Or expected if the function is well behaved. So if it is shrinking, it should shrink in a systematic order. And if it doesn't shrink, then also the only thing is it will rotate. If something and that's the length, the same length is there. If there is this length and this length are the same, in that case, if I take any point, I take another point, it would move with this. It will not move somewhere here. The same length will be maintained. And that is basically what all this is about. And as can be expected, if the function is well behaved, I cannot have this. Either it is shrinking or maybe with the same length. And of course, it cannot be larger here. So let fz be analytic in mod z less than 1 with f of 0 equal to 0. If the value f of z mod is less than 1 in mod z less than 1, then f of z mod would be less than equal to mod z in the unit disk. And if at certain points, at some point, f of z naught and mod z naught are equal, then your function, I can even get what that type of function is going to be. It is going to be lambda times z, where lambda in modulus is 1. So it may be something like e raised by theta, some formation of this quantity, which so that mod is going to be just 1, and theta would be the corresponding rotation. So it would be just rotating and so on. And if fz is not of the form lambda z, then f dash of 0 is going to be less than 1. That's the other result. Now, what does this signify? If f dash of 0 is less than 1, what does this signify? Let's try to analyze this wording. I want to look at this quantity. 1 minute. Just 1 second. Yeah. Let's try to analyze what we mean by the word f dash of 0 modulus less than 1. F dash of 0, if you look at, it means limit f of 0 plus h minus f of 0 over h as h tends to 0 is 1. Or in a neighborhood, so f of h minus f of 0 over h is approximately equal to 1. Sorry, it's less than 1. So this is less than 1. Call it as some number. Let's just for as an example, let's take it as half. So approximately equal to half. Just to give an idea. So it's approximately this. So if I bring this h here, so what you get is f of h minus f of 0 in modulus is approximately half mod h, right? F of 0, we are taking as 0. So we have mod f of h is approximately half mod h. So let's try to visualize what is happening. That's the point, say 0. Naturally, this is 0 and that's your 0. And there's your point, say some h. So this is length that we are having from here to there is mod h. F of h, the value f of h is half of that, approximately half of that. So that was your h length, so it would be here. So that would be approximately where your f of h would be. So observe what is happening is the point h under f moves up here, or it is contracted. The point comes closer and closer. Had the h been here, your f of h would have been somewhere here. It could not be somewhere up here. It had to be here. So it gets contracted. So this gives us a contraction. So in fact, it's known that 0 is an attracting fixed point that comes up in many other cases. If you have studied complex dynamics or dynamics, you may have heard this word, attracting fixed points. So this is what is happening. It tells you that the point is attracted towards 0. So this is what we are trying to emphasize here, that if the function is well behaved, then and is mapped from unit disk to the unit disk. In that case, every point that I take, the points come closer and closer, in fact, nearer to this quantity than this quantity. And if it remains at the same quantity, then it is just a rotation. So if fz is not of this form, then the points get attracted. So that's your Schwarz's lemma. Another interesting result is the maximum modulus theorem. And if you observe, if I take a diagram like this, and I take its image like this, then if I take a larger disk, our expectation is, because that is inside, it should be larger. Observe that this may happen, all right, if our function is well behaved. If it is not well behaved, if the function was arbitrary, I could have taken a point from here to here, a point from here, somewhere here, a point from here to here, and so on, arbitrary. A quantity here and then here, and so on. But the function is well behaved. So all these things are not possible. So we would expect a larger quantity given this quantity. And this is what the maximum modulus says, that fz be analytic, then fz cannot attain its maximum inside D, unless it is constant. Because if it's constant, then of course everything will be the same number k, constant k. So there's nothing. But other than that, if the function is well behaved, the quantities that we are talking about here, the maximum value is this quantity, maximum length modulus is this quantity. And naturally, corresponding to this, I am having this diagram, and our maximum would be something here, larger than that. And that is what it is all about. So let fz be analytic in a region D, then mod fz cannot attain its maximum inside D unless fz is a constant. Geometrically, let's try to, there's a symbol here, MRF is maximum of fz on mod z less than equal to. What does this mean? Because this is quite an important terminology that is used in many places. So let's try to analyze this particular term. What does this stand for? Let's take a circle mod z less than equal to R. Okay. Let's take a circle mod z less than equal to R. Then I draw its image. Of course, and remember, continuous image of connected is connected. So I'll get just one piece because I've taken just one piece. So you'll get some connected piece. Right? So I obtained this point. Now, this length is your R. So if I take any Z here, then there is a corresponding f of Z here. And this length from here to here is modulus of fz. Now I take the maximum of all these. Maximum on mod z less than or equal to r. That means I take all the points, I calculate these lengths at the origin from all the sides, and whichever is the maximum, I call that, for example, here it is this one. It may be this one, the maximum. I call this length by m of Rf. The maximum length that we have is denoted by m of r. So this is your m of Rf. So if I take this portion, I take its maximum, I denote it by m of Rf. So if MRF is maximum of Fz on mod z less than or equal to r, and as we already seen, that maximum is on the boundary. Naturally, if I have a larger disk here, I'm interested in the maximum corresponding to this. So maximum has to be on the boundary. So the diagram that we get would be something larger, and this would be your maximum. So if I call this as, the first one is R1, and this is R1, and this as R2, then this would be your M of R2. M of R2F. So obviously, if R1 is less than R2, M of R1F would be less than M of R2F. In fact, equality will come up only when the function is a constant. Otherwise, it will be strictly less. If this quantity is strictly less than, this answer will be strictly less than, unless the function f is a constant function. So obviously from this, we can observe one thing is that if as r tends to infinity, m of Rf will tend to infinity. The larger the disk, larger is the diagram here. So bigger is your portion. And you can keep on doing this indefinitely. So MRF tends to infinity as r tends to infinity. Here, if you observe, I took the diagram with the portion here in this way. I could have taken the image. Is not necessarily should contain the origin. It could have been here. The origin here. It's not necessary that the origin should be inside it. It can be outside also. But even then, when I take a larger disk here, I would expect a larger piece here. So in the first case, your MR1 was this much. In the next one, it is this one. So for R1 less than R2, M of R1 will be less than M of R2, corresponding to this very well behaved function f, or analytic function f. The next, once this is there, of course, we can, it means here M of Rf tends to infinity as R tends to infinity. Now, once it is tending to infinity, a lot of problems do arise. Let's try to look at it. Let's try to look at it. We know very well, let's say f of r is r square, and say g of r is maybe r cube or r to the power of 4. Let's say even this may be 8 times r square. We know that the portion fr by g of r will tend to 0 as r tends to infinity. Or you can say that fr is growing at a slower speed. Fr is growing at a slower speed than g of r. Or you can say gr is tending to infinity at a faster rate. So even though both of them are tending to infinity as r tends to infinity, but there is still a comparison in the sense that this is growing at a faster rate than your r square, 8r square, even though there is a coefficient. Now the same thing happens when we are talking about m of rf. We know that it is tending to infinity. Now f may be a polynomial or maybe translate an entire function. So there are different ways in which it can tend to infinity. So the question comes up, which one tends to infinity at a faster rate, whether it is polynomial or which is translate an entire function. So for that, we have to calculate the MRF corresponding to it and the MRF corresponding to this quantity. And this can be calculated that if we are having Pz or a polynomial Pz to be an z to the power of n plus an minus 1 z to the power of n minus 1 plus and so on, then modulus of p of z will be asymptotic to modulus of an r raised to n, where mod z is your r, as of course as r tends to infinity, as r tends to infinity. So we can always look at it and show this quantity. And it is interesting that e raised to z, that exponential or transcendental entire function, will grow at a faster rate than this. So let's go back. So that is there. Okay. Okay, I'll be coming back to this result a little later, but let's move ahead. So here, let Pz be equal to a0 plus a1z plus a2z square plus anz to the power of n be a polynomial of degree n. Then MRP is asymptotic to an r raised to n as r tends to infinity. And let f be any transcendental entire function, then no matter what polynomial I take of whatever degree, it may be a very big degree here and may be very large, but still MRP over MRF will tend to 0. That means the transcendental entire function grows at a very fast rate than your polynomial. So this quantity grows at a very fast rate in comparison with this quantity. In fact, so this leads us to define a new term called as order. Where because this is tending at a faster rate, so obviously it has to be faster. I want to compare it. Let's say I want to compare MR of f and another function MR of g, both transcendental. I want to compare this as well as this. How do we compare these quantities? I cannot compare them with a polynomial, because if I try to compare a polynomial, this divided by MRP will tend to infinity. This divided by M of RP will also tend to infinity. So which one is tending to infinity at a faster rate? I don't know. So something else has to be done so that we can work and try to compare this function f and g and tell which one is growing at a faster rate. And that theory is a big theory which involves the growth of entire functions. It's known as the growth of entire functions. The whole theory starts with that. Now, for that, again, let's go back. We looked at MR of P, or in fact, MRF over MR of P, which is asymptotic to MRF over modulus of A and R raised to n. And this result was tending to infinity. That is, this quantity is tending to infinity. But once this is tending to infinity, it means if I want to compare, say, F and G, naturally I have to compare with something larger than R raised to n, because R raised to n will always give us the answer infinity. So I should try to compare it with something more than that. In fact, the next best would be your exponential, G raised to R. And that is basically what happens. We talk about the order of an entire function, rho, as given as limit log MRF over log of R, as R tends to infinity. And this is called as the order of F. So order of an entire function F is defined by limit square log MRF over log of R. For a polynomial, if I use the order of a polynomial, comes out to be 0. And that's quite simple. You can just look at it. This was asymptotic to A and R raised to n. So if I take the one log, it gives you, this gives you n log of R plus mod log of mod an. If I take the second log, gives you log n, and then log R, log n, and then log R, and log of the quotient. Once I divide by log of R, there's two logs here, and log R in the denominator. So this quantity will tend to 0. Constant divided by log R tends to 0, and constant divided by log R tends to 0. So everything tends to 0 on the right-hand side. So the order of a polynomial is going to be 0. Then the other thing comes up is, what about the others? Order of F. Now, many times the order of F may be 0, it may be 1, or it may be infinity. In fact, there's a theorem which says that given any n, it can be not necessarily in this, given any, say, n in positive integer, it can be, it can be rational also. Given any k in the set Q of rationals, there exists an entire function f whose order is exactly k. So the number of entire functions you can see is quite large, and given any k which is rational, we can always get an entire function with that particular order. And why this was being used, I think I'm almost coming to an end because I've almost exhausted my time. We have a lot of relations regarding it. If the answer becomes infinity, let's just try to complete it here. If it is finite, there's no problem. Let's say if it's 3, there's no problem, I can tell. But if it is infinity, then question comes up, what do we do about that? In that case, we talk about another log, 3 logs on this side, because remember, log will make the speed slow. So the speed is decreased. So this may be finite, some finite number. If it is not, if it is still infinity, I can take n that log and so on. And suppose it becomes 0. Or in that case, I would like to get some number. So why not increase it here? Log r. So in fact, we can talk about pqth order of an entire function. Entire function. Pqth order of entire function. So p logs on the numerator and q logs on this side. And then we can talk about, so that we get an order, and then comparison can always be done. So in fact, it's a big theory. A lot of work is being done on this particular topic, which I will not go in because we are already running short. But I had mentioned that we go over this particular result on the minimum modulus theorem. Let f be analytic in a region D, let fz be not equal to 0 in D, then fz cannot attain its minimum inside unless f is a constant. So basically, it again says the same thing. If I have its image, a quantity like this, obviously the minimum is going to be on the boundary. And in fact, this is your minimum value, modulus, straight line. So this is your M of RF. Observe the image of this could also have been like this. But then f, if there is some quantity is coming here to 0, the minimum will always be that, it can be anything that we want. So we want to avoid this type of situation. For that reason, we are basically interested in this type of relation. So that's why we are taken, the function should not have a 0 inside. So let fz be not 0 in D, then fz cannot attain its minimum inside D unless f is a constant. If it's a constant, naturally, every value is going to be the same constant. Every value is the same. So maximum, minimum, everything is going to remain the same key. So that is not the important one. So normally, if it's not constant, then the maximum and the minimum will always be on the boundary. For the minimum, we will require that the function should not take any 0 inside. But for the maximum, there is no restriction. It can be containing the 0 inside or outside. It makes no difference. The maximum is always on the boundary. So these are some of the results that is there. So these help us. So we define the order. Let f be an entire function. Limit square log MRF is called as the order of f, and limit inferior log MRF over log of r is called as lower order of f. And these help in studying the growth of entire functions. And entire functions, as we have mentioned, are well behaved. So a lot of expectation is there from the entire functions that the results, what we expect is what we should get, we get. And in fact, it also helps us in another way, because now we know that it's very well behaved. So naturally, if we expect something, whatever it is, just as I just said it here, our expectation is this quantity. So we try to prove it. When I take a quantity like this, if it's well behaved, I do not expect it to break up, right? This I do not want. We don't expect an answer like this. It's okay if the function is not continuous and many other things come up, but if it's well behaved, this type of things is not possible, may not be possible, and it doesn't happen. So what we expect is what we get. So from that point of view, your analytic functions are very well behaved functions. So I hope you've got some idea, and maybe you may motivate your students and maybe do some more research on your own and try to see what other properties are there where the functions are well behaved. So with this, I close my lecture. Thank you very much.